We can use this principle another way. Let's look at an example here. Let's say we have a tube, U-shaped tube, and I put water in one end, and I put oil in the other end. Water and oil don't mix, right? Dr. Ibrahim has taught you that? Okay, so we know that the pressure of the oil, or sorry, the density of the oil is different from the density of the water, right? Okay. Now we know that the pressure here coming from the oil must be the same as the pressure on this side coming from the water, right? Okay. Otherwise, this interface would move. So notice what happens. We have a different height from the water than we have for the oil. Okay. Same point. Well, it's not exactly the same volume, right? Okay, it may be the same mass, and that is what is keeping this interface here. Okay, constant pressure. Okay, so if we have the same mass but we have different densities, then what is the height of this column going to be relative to the height of that column? So the pressure from the water is P naught plus rho of water times G times the height of the water, right? And that must be equal to the pressure on the other side, which is P naught plus rho of the oil times G times the height of the oil, right? So P dot is the same on both sides, G is the same. So the height of the two columns will be inversely proportional to the ratio of the densities. Okay? Okay, now, next principle in fluid statics, Archimedes principle. Archimedes principle tells us that if I immerse a solid in a liquid, the liquid will react with a buoyant force. Okay? The buoyant force is upwards, and it's equal to the weight of the water displaced, or the weight of the fluid displaced, because this is valid for any fluid. Okay, so that's a fairly simple principle. And if you have trouble believing it, just imagine a thought experiment. Think about, before you've added your solid, you have water, or you have fluid in the same volume, with the same shape. And it is feeling pressure from all sides. And from Newton's second law, we know that this is a static fluid. So the net forces must be equal to 0. So the net buoyant force must be countering the weight of the fluid. Okay, so if I replace that fluid with the solid, it's going to feel exactly the same buoyant force. Now, suppose I have a gold statue, and I choose to immerse the statue in water. Now, is the statue going to float, sink, or is it going to be partly submerged? It's going to sink. Why?
Because
it's denser than the water, right? So the buoyant force will not be enough to pull it up. But now, if I immerse it here so that I have a string at the top, then with the tension in the string, I can submerge the statue, but still hold it up from the bottom. Okay? So now the question is, what will the tension be in the string?
the force minus the
So we know sum of the forces equals 0, right? And the free body diagram is here. It tells us tension plus buoyant force minus mg will be equal to 0. So the tension is going to be mg plus the buoyant force. Minus the buoyant force, yes. Now, the buoyant force is going to be equal to the weight of the fluid displaced, right? So this is rho of the water times the volume of the water times g. Okay, so, and notice mg is going to be rho of gold times the volume of gold times g. So this is equal to rho of gold minus rho w times v times g. Right? Right. Okay, so here we've given the statual weight, and we calculate through, and we get the numbers. We give the statual weight of 15 kilograms, and then we divide by the density of gold to get the volume. And from that volume, we can substitute that in order to get the buoyant force. Okay? Or we could have just gone here and taken the difference in the densities and multiplied by the volume by g. However, we would have still, in this case, had to calculate the volume because it's giving you the mass and not the density of the gold. Okay? Okay, so the important concept here is simply that the buoyant force is equal to the weight of the fluid that's displaced and not to the weight of the gold. All right, now we're going to move from fluid statics to fluid dynamics. Okay? So what's so funny on this slide?
We had two chapters in ثانوية عامة, secondary school. We took this two chapters in about 2 months.
So we just skip this slide. Okay, so let's just go through it quickly. Let's review it. Suppose I have this toothpaste tube, and I ask you, what's the volume of toothpaste that's on this side of where my hand is? How would you calculate that? It's kind of a funny shape, right? So the other thing I can do is I can make use of the fact that if this is a fluid, and it's incompressible, then when I open the tube here and I start to press it and toothpaste comes out the other end, the amount of toothpaste that I remove from here has to be equal to the amount that comes out here. Yes. Right? And the amount that comes out here I can calculate, right? Yes. Because I can measure the diameter of the outlet and I can measure the length of the tube that comes out. Okay? So this is the kind of thing we can do with the continuity equation. And it's just based on the same principle. If I have an incompressible fluid, then the amount of fluid, and it's moving, then the amount of fluid that's coming in from this side has to be equal to the amount that's coming out from the other side. So, I can say that dV1 is equal to dV2, and dV1, if I'm asking, let's say, the amount of fluid that passes through a particular surface area in a time t, that's going to be equal to area 1 times delta x1, where delta x is the path that the fluid has traversed during that time. And that delta x is equal to v times delta t. Okay? And the same coming out the other end. Okay, so this is a2 times delta x2. So I can say that a1 times v1 delta t is equal to a2 times v2 delta t. Okay? So we call this the volume flux flow rate, the area times the velocity. Now, did you study Bernoullis equation?
No.
In high school?
No.
Okay. Bernoullis equation, but Bernoullis equation you can understand very readily. Bernoullis equation is just applying the conservation of energy to a fluid flow, or actually I should say the work energy theorem. So let's say we have an incompressible fluid. And it is, so I guess I'm supposed to write on this side. You guys, some people can see over here? Okay, so I'll write over here. So, imagine we have a fluid flow as we see in the figure. Now, in a given amount of time, we're going to have a displacement of the fluid, ds here. ds at the top may be a little bit different, if the area is different, right? And then I can say that in that given a period of time, the work done will be equal to change in kinetic energy plus change in potential energy. Now, the work done during this time will be the work that's done over here. So that will be F times ds. And the force is equal to the pressure times the area. So that's P1 times A1. And then multiplied by ds1. Okay? So this in turn, A times ds1, I'll call dv. Okay? And notice I'm not calling it dv1. Why? The same volume displaced all along. Right? Okay?